Hello, good morning, good evening, students. So we were doing a crash course on chemistry for the upcoming J exam, and we were in the chapter thermodynamics. So in the previous chapter, in the previous lecture, we have studied the first law of thermodynamics, which says that the total internal energy change in a system is equals to the work done plus the heat that is transferred to that system. Now, today we will mainly focus on the second law, but before that, let us study a system that is a cyclic process. So what do you mean by cyclic process? So if you see a process that starts from a, say we start from a state 1, goes around to various states like this, from say here to here to here. So let us say it is state A, state B here, then your state C, and suppose we have various number of states that we go through, and at last we move to this last state, the for initial state, which is A. So for this type of process, in which we start at some initial state, then we move to different states and move back to the initial state, then this type of process is called as a cyclic process. Now what are the characteristics of the cyclic process? The first characteristic is that the net change in a state function is always zero. So what is state function? We have studied earlier also. So state function is something which depends only on the initial and final state. So initial and final state means, what does it means that we have to if we have to calculate the change in this process that is going one round, so we are considering only one round from here to here, then suppose we have to calculate delta H, which is enthalpy. Now what is delta H? So since it is a state function, we will not calculate enthalpy change for this, for this, for this, for this, or for anything. We will simply calculate H, that is here at A. So HA. Therefore delta H can be calculated as delta H is equals to HA. And since the initial and the final state are same, so the initial state is, since the initial state is HA, so final state will also be HA. Means the enthalpy of that system will also be HA. This results in 0. For that reason, all the state function around a cyclic process will be always 0. So if you want a more simpler example, let us take the case of temperature. So since it is a PV diagram, so for this point, PA is equals to VA. Sorry, PA is equals to P initial is equals to P final is equals to PA. Similarly, VI is equals to V final is equals to VA. Now since pressure and volume are same, so pressure and volume are same, and I have told earlier that we are only considering that we are taking a system which have the same number of moles, and also if P, this is a kind of mentioning a state, so if we have mentioned the P and V, so T will be also same. R is a constant. Now since these both things are constant, as we are always taking a closed system, or you can say isolated system, so this T will be the same, so it will be TA. Now so for both of this initial and final, that is T initial is equals to T final is equals to TA. That means if we put it P initial here and P final here, and if we calculate, we will get the same. So temperature will also be same. So for that reason, T initial will be TA, T final will be also TA. TA minus TA will be 0. So you can see here clearly that since it is a state function, the temperature, the volume, or you can say the enthalpy or the internal energy, there the net change in the cyclic process will always be 0. Whereas for the path function, it can or cannot be 0. So both can be the case. So it is not necessary that it will always not be equals to 0. For some cases it can be 0, or for some it can be negative or positive or any random value. So this is a cyclic process. Now we will take an example of a cyclic process which is called a Carnot cycle. So what is it is an example of cyclic process, of course. Now what does this Carnot cycle consist of? So in this Carnot cycle, 4 steps are taken. What are those? So first is the isothermal. First is the isothermal expansion. So from one state to two state, we do here the isothermal expansion. Then in the next This is the isothermal expansion. Then in the next step, we do the adiabatic expansion. Third step, we move to compression. And again, we do the adiabatic compression to move to the initial state. So since we are seeing here that we have started from state A, move to state 2, then to 3, 4 and back to 1. So we are doing a cyclic process, kind of cyclic process here, because we are just starting from state A, say we are starting from state 1 and we are moving back to that initial state. So Carnot cycle is a cyclic process. Now, why do we do this Carnot cycle? So this Carnot cycle thing is mainly found in this heat engine. So in the heat engines, we use it to calculate the efficiency of that heat engine. So I will deal with this thing in the next slide. So what is efficiency? So if in short you can say that what is the output we are getting after we are giving some minerals or some minerals in burnt in it. So what is the output of it? So for that reason we are using this adiabatic this kind of Carnot cycle. So in that process, a cycle took place. So means a cycle takes place. So we use this Carnot cycle to calculate the efficiency. Now, the more important thing here is that we have to calculate the work done for each and every step. So the first is the isothermal expansion. So in the first process, we do the isothermal expansion. Now we know the formula for work done. So from first law, we know that delta U is equals to Q plus W. Now, since the process is isothermal and we know that delta U is equals to NCV dt. Therefore, NCV dt is equals to, since this is equals to 0, so this is equals to 0. Now, one more thing important is here is that all the processes that are taking place, whether that it is adiabatic expansion, adiabatic compression, or isothermal expansion or isothermal compression in a Carnot cycle, all processes are reversible. So we will always calculate it for the reversible case. Now delta U is equals to Q plus W. Therefore, Q is equals to W minus W. And we know that for a reversible case, it is equals to nRT ln V2 by V1 with a negative sign. So it will be overall nRT ln V2 by V1. So in this way, this is the formula that is given here. That is Q1 is equals to minus W1. So in this way, you can calculate the work done for this first step, that is the isothermal expansion. And that is done with temperature T1. Yes, this is having a temperature T1. So since it is isothermal, the temperature will kept constant. Now, next is what? Next is the adiabatic expansion. Now, since it is adiabatic, we know that adiabatic means Q is equals to 0, and we know that delta U is equals to Q plus W. Since this Q is equals to 0, therefore delta U is equals to W. Now, we know that delta U is equals to NCV dt. Here we are moving from temperature T1 to T2. So it is written here, sorry, this is T1 to T2. So we are moving from T1 to T2. Therefore, work done will be NCV T2 minus T1, and this will also be the internal energy change. So this is the next work done. So what W2 is equals to this one. Now similarly, we are again doing a isothermal compression. Here will be a negative sign. Oh, sorry. Okay, it is right. So this is okay. Okay. So we are moving from V2 to V1. So what we are saying is that we have started from a temperature that is T1. So for isothermal, this will always be T1. Now we'll move to adiabatic compression, sorry, adiabatic expansion. So this will be gone from T1 to T2. And then again, we go for isothermal compression. Now since temperature is kept constant, so it is T2. Okay. And ln V2 by V1. So this is the diagram for it, and this is the equation. So similarly, we will again write this equation. Now again for the work done, it will be CV by T2 by T1. Now this is the formula for efficiency. So what is efficiency? So efficiency is nothing but eta is equals to 1 minus T2 by T1. So it represents the ratio of the work done by the engine to the heat absorbed from the high temperature reservoir. So why I'm considering reservoirs, this thing called efficiency will come in the to know in the later slides when we will study this second law of thermodynamics. So second law of thermodynamics deals with this efficiency thing. So we'll study in there in brief. So first of all, why was first law of thermodynamics rejected? The first thing with the thermodynamic first law of thermodynamics, the problem was that it does not talk about any dissipation of energy. Means in the previous slide we have seen that we were dealing with the efficiency of a Carnot cycle. So efficiency means the amount of energy that we are giving to it, or the mineral you are giving to it that is burnt, and the work that is produced is not necessarily equal. So there is some kind of dissipation or in the form of, you can say, heat, or in the form of sound. So this energy is lost. But in the first law, so nothing like that is mentioned. It simply says that for del U is equals to Q plus W, which means all the work done and the heat transfer are converted to the internal energy. It does not talk about the dissipation thing. Now, first law of thermodynamics is another thing that is wrong. So it does not talk about the flow of heat of energy. In which direction that energy will flow. Means suppose we are taking a hotter body H and a colder body T. It does not say that when they are connected to each other, heat will flow from which direction to which direction. So it does not talk about the spontaneity or the direction of the process or the direction of the heat flow. Now we will move to the second law of thermodynamics. So second law of thermodynamics is mainly associated with the inotropy. So there is a thermodynamics variable called inotropy. So what is inotropy? So inotropy is in NCRT, if you see, it is mainly referred to as the randomness, or you can say that in what more fashion a system can be arranged such that the energy will not change. So you must have studied about this delocalization of the electron. So you have seen that, okay, so if you want to make a thing stable, it should be delocalized, means the electron should be moved from one place to another, that it can move from one energy to another energy level, so that it can be distributed along more than one atom. So when it goes from one state to another, means one atom to one orbital to another orbital, when there is enough less gap of energy, though that it can travel from one place to another. So the basis of that you can say stability is that is lies with the entropy. So entropy also says that if a system can exist in more than one state for a given energy, that means degeneracy you can say, then the more is the degeneracy, more is the stability of the state. And if you want in a very easy manner, you can say that it is the state of randomness. So more is the system is random, or you can say more the heat is distributed, that system will be more stable. Now, for a process to occur is spontaneously, the entropy of the universe should increase or remain constant. Sorry, remain constant. So it says that suppose a reaction has to happen spontaneously, because which means there will be no external factor applied to it. It does not mean that we cannot apply it initially. So suppose you have a fuel and you lit it with fire. Now you have just initiated that reaction, but you are not say you are not moving it to an external environment furthermore, and you have only initiated it. So for that case, the burning of fuel is also this kind of spontaneous process. So for a spontaneous process to occur, the entropy should increase first of all, or it can remain constant. And what is the entropy of universe? So it is equals to system plus surrounding. So we have two parts. So whenever you are considering thermodynamics, you have two parts. The first one is the system, and the second one is the surrounding. So delta S universe is equal to system plus surrounding. Now we'll talk more about inotropy. So first we have seen that when a system will be spontaneous, so it says that when the total inotropy of that universe is increasing or remaining constant, then that process will be spontaneous. Now what is this inotropy thing? So we have introduced this inotropy thing. So if you the simple meaning is that it is the quantity that measures the disorderness or randomness of a system. So how much a system is disordered or random. Now it is also the number of way in which the energy of a system can be distributed, the same as the delocalization of the electron. And what is the formula for delta S in entropy? It is dq by dt. Now it can be greater than dq by dt or equals to dq by dt. So we'll see the different cases when it will be equal and when it will be greater than. So this is a general formula and not the means typical formula you see everywhere, that is del S is equals to dq reversible by t. So it will come in the later slides, but this is the more general formula, that is del S is equals to delta S is equals to greater than or equals to dq by t. Now some of the properties of inotropy are that it depends upon a mass of the system. Of course, it is an extensive property, so it will depend upon the mass of the system. Now the next most important point is that it increases with the increase in temperature. So do not assume with the formula that since delta S is equals to dq by ds is equals to dq by t. You can see that it is, yes, it is inversely proportional. So this and this are this, if this will increase, so this will decrease. So this is not the case. So the formula you see here, it is not for the absolute entropy, but it is for the change in entropy. So change in entropy is of course inversely proportional to temperature, but absolute entropy is directly proportional to temperature, means it increases with temperature. So that's the main point over here. Now entropy order is simply gas is having the most highest entropy, because if you see a gas, it has more randomness, it can move anywhere at any place. Then we have the liquid, then we have the solid. So how are we relating randomness to the number of states that are available? So if a system is, suppose it is random, now let us uh, get a more depth idea of the entropy. Suppose a system is random, means it can move here, it can move here, it can go there, means it can be placed in any place. So let us consider another case. So the molecules are more random, so it can move anywhere. So that is the idea of randomness from your perspective. Now if you consider the energy part here, you can see that this both, so suppose it is the energy of A, it is the energy of B. You can see that energy of A is approximately equals to energy of B. Why is it so? Because means the particles are moving from here to there without any external factor if you see in an environment. So with this increase in randomness, there is a more probability that a system can be existed in more than one way, and still it will have the approximate same energy. And due to this availability of more number of states, a system is more stable. That is the reason for the stability of a system. So in this way you can relate randomness with the stability, and you can see that same thing in the delocalization also, that the electron can be here also and here also. For that reason its inotropy or randomness is increased, you can say, and it becomes more stable. So let us move to the next thing. Now we have the reversible process. Now if you calculate that if you want to know that what is the value for reversible process, now ds is equals to dq reversible by t for reversible process. And what is ds? Suppose we are calculating it for the universe, so it will be dq reversible surrounding minus dq reversible, this one will be reversible surrounding plus system. Sorry for the mistake. So it is written here that if you want to calculate for reversible, so for reversible ds is always equals to dq by t. Now if you calculate it for the universe, so universe it will be system plus surrounding. For the system, suppose a system is there, like this. So this is the system, and it is giving dq amount of heat. So what is the amount of heat that is lost by dq this system? So it will be minus dq. And what is the amount of heat that is gained by the surrounding? It will be always plus dq, which means that whatever the system is losing, the surrounding is gaining that same amount of heat. For that reason, we can say, just this is the surrounding here, that it will have the same magnitude but just the opposite sign. So I've used the same concept here. So suppose we have a system here. That system is losing a dq amount of heat. So let us write it for more easily, so you do not get confused. It is for system. So we know the formula. So if you calculate it for system, so it will be q reversible by, suppose the system is getting dq amount of heat. So it will be dq reversible system by T. Now the surrounding is getting that heat. So it will be minus dq by dt. Now, since it has opposite sign, this both will get cancelled with each other. So for reversible process, you can say, always say that the overall entropy change or the entropy change for the whole universe will remain constant. Whereas for irreversible process, it will be always greater than, so irreversible process, it will be always greater than ds. So dq irreversible by T is always greater than ds. Now let us calculate the entropy change. Now let us calculate the entropy change in a reversible process, which is, now we are elaborating the formula more, means elaborating the formula more. So from first law of thermodynamics, we know that total energy change, that is du, is equals to dq plus dw. Now, if we find out the dq, then it will be du minus dw. We also know that delta u is equals to ncv delta t, and w is equals to p delta v. Now, if you put from the second law of thermodynamics, so that ds is equals to dq by dt. So if we integrate this equation, so you will get this. Now you know that dq is equals to du minus dw. We know this equation very well. It is ds is equals to dq by dt. Then we will put this thing here. So it will be du minus dw. Now you're using equation 2 and 3. So we know that du is equals to minus, sorry, ncv dt, ncv dt, and dw is equals to minus pdv. Now, if we write it here, so we will now put this formula here. P is equals to nRT by V for P. So we have just put this apart. So let me do it clearly for you. So suppose we know that dq is equals to du minus dw. So from the first law of thermodynamics, we can write it. Also, we know that ds is equals to dq by dt, dq by t. So it is all for reversible. So we are calculating it for reversible because the formula is for reversible only. Now we know that du is equals to cv dt. So for 1 mole, we can write it cv dt by t. So this is for ds. Now dw is equals to, we know that dw is equals to minus p dv. So this is equation 2, this is equation 3. So from equation 1, 2 and 3, I am writing directly. So dw is equals to minus p dv minus p dv So later on we can write that Cv dt is equals, so we are putting Pv equals to nRT, so P is equals to nRT by V. So it will be simply nRT dV by V. So this is the final equation. Now we'll integrate on both sides. This will give, so suppose we are calculating it from S1 to S2. Here it is for T1 to T2, and this is from V1 to V2. So it will be delta S is equals to Cv ln, so ln T, it will be between limits T1 T2, then it will be nR T ln V1 V2. So we are putting a more general formula for here. So it will be Cv. So you know that ln T2 minus T1 is equals to ln T2 by T1. So if you put the limits here, that is ln T2 minus T1, so it will be ln T2 by T1. Hi Tanvar Sanju. So it will be nRT ln V2 by V1. So this is the final formula we got. The same thing is written here. It is for n moles. So we can write that for n moles, we can write NCV ln T2 by T1 plus nR ln V2 by V1. Okay. Now we will move to the next thing, that is for isothermal reversible. Now we will take different cases of irreversible processes. So we know that the formula for reversible is NCV ln T2 by T1 by nR ln V2 by V1. Now since T2 is equals to T1 and we know that ln, so it is like this, NCV ln T2 by T1 plus nR ln V2 by V1. Now since T2 is equals to T1, therefore ln1 is equals to 0. So this value will be 0 of all. So it will be finally nR ln V2 by V1. So this is the final formula. Now if we consider it for an isobaric process, so we know that delta S is equals to NCV ln T2 by T1 plus nR ln nRT ln V2 by V1. Okay. nR ln V2 by V1. Now we know that P1 V1 is equals to P2 V2. Okay. So we can write here V2 by V1 is equals to P1 by P2. Now since it is an isobaric process, if we substitute this thing here, that is P1 by P2, now P1 will be equals to P2, so it will be 0. So the final formula will be NCV ln T2 by T1. The same thing is written here. So nR ln T2 by T1. Now for an isochoric process, we will use the same. So we know that V2 is equals to V1, so the formula reduces to this. Now if we calculate for an isobaric process, we know that adiabatic process, we know that the initial formula, we know that delta Q is equals to delta Q reversible A by T is equals to entropy. Now since this Q is 0, so this delta S will be also as 0. Now let us move to phase transformation. So whenever you do a phase transformation, one thing should be kept in mind always. So suppose you are going from solid to liquid or liquid to gas. So if you see in your environment, so you always see that it happens at equal pressure, that is 1 atm. Suppose the pressure is mentioned 1 atm, so I'm taking this case. So it will always happen at this constant pressure. So for constant pressure, we have a formula. So we use that formula always. Now delta S is equals to Q reversible by T. We know this. Now since this thing is happening at constant pressure and we know that delta H is equals to QP at constant pressure, you know that very well that at constant pressure delta H is equals to QP. So it will be simply delta H by T for any transformation we consider. Now this is the first one we are taking. It says that it is the entropy of fusion. So what is fusion? So it is the change in entropy when 1 mole of a solid substance is changed into a liquid at its melting point. So we know that delta S fusion is equals to S solid minus S liquid. So since we are going from solid to liquid, so solid is the final state, so it will be S liquid minus S solid, that will be delta H fusion by T. So here we are using the enthalpy of fusion here. We have derived the initial formula that yes, delta is equals to del H by T at constant pressure. Now similarly, if we are doing the vaporization, we know that delta in vaporization, what happened, that liquid changes into gas. So what will be the change del entropy change accompanying it? So it will be S vapor minus S liquid. Now since it is happening again at constant pressure, so delta H vapor by T at the boiling point. Yeah, one more important thing here, that it will take at the boiling point, of course. So it will be delta H vaporization by T BP. So how is it so? So suppose we are calculating it for water. We know that the boiling point of water is 100 degrees Celsius. Now suppose the transformation takes place, that the water which is in liquid form changes to water which in gas form at constant pressure, which is 1 atm. So we are taking 1 atm. So at 1 atm, what is the boiling point of water? So boiling point of water at 1 atm is always 100 degree Celsius, or you can say 373 Kelvin. So if you want to calculate the delta S accompanying it, so it will be delta H by T. We know that we have used the formula. Now we will simply put this delta H vaporization, which is delta H vaporization of water, upon 373 Kelvin. So this is for 1 atm pressure. So the pressure is 1 atm here. So in this way you can calculate the entropy change accompanying a vaporization of water. Now next we will move upon to sublimation. So what is sublimation? So in sublimation, solid directly changes into gas. So in entropy of sublimation says that when 1 mole of a solid changes into vapor, then the entropy accompanying it is called as entropy of sublimation. And what is it equals to? So delta sublimation is equals to vapor minus liquid, as we are moving from liquid to vapor, and vapor is the final state. So it will be vapor minus liquid, which will be again equals to delta H vapor by T BP. Now you will move to a next more important thing, that is standard gives free energy. So before moving to it, why do we introduce this entropy thing? So we saw that initially we know the direction of flow of heat, but we do not know that why the where the heat will flow and why the reaction is happening. So suppose water is falling from a top height, then why does it occur and why does it flow in that direction only? So to analyze or to check the spontaneity or the direction of reaction, we introduce this in a entropy term. But we have seen that for a reversible process, okay, it is possible to do this thing to calculate in entropy, but in actual all the processes that we see or do is always an irreversible process, and reversible case is an ideal one. And we have seen that we cannot calculate the actual inentropy change. Why? Because suppose we can calculate it for, you can say, you can calculate it for the system. Of course we can calculate it for system, but it is much more complicated to calculate it for the whole surrounding. And for that reason we introduce this delta G term, which will make our things more easier. So this is the main reason behind it. So we know that delta S, when it will be spontaneous, so it will be spontaneous for reversible process, it will be greater than 0. And for this thing to happen, we have to check the delta S for surrounding, which is not practically possible. Is equals to what? Not practically possible. Now due to this reason we have included this Gibbs-Helmholtz energy. Now what is Gibbs-Helmholtz energy? It is a measure of spontaneity of a change under a specific condition. So if you know the formula, it is simply delta G is equals to minus RTL in case. So this is the relation between the equilibrium constant and the delta G. Now it can be also calculated using this formula, which says that delta G naught is equals to product minus reactant. Now let us see some questions to make our things more clear. So before that, let me introduce the new formula of delta G, which is delta G is equals to delta H minus T delta S. So it is the formula which will be used to know the spontaneity. So we'll learn this spontaneity thing in the next chapter. So before moving to that, I have left some topic yesterday, so I will cover it today. So let us delve more into the first law of thermodynamics. So what does the first law of thermodynamics says? It says that the total and internal energy change is equals to Q plus W, which is the heat transfer to the body plus W. What is the heat change? So heat change is the amount of heat that is transferred to a body. So heat is basically something that changes the temperature. Then it is the addition of work done gives the total internal energy. Now we have seen many formulas for it. So let us revise it. So we know that Q is equals to NC dt. So we'll take this d here for small heat of charge. It is dq is equals to NC dt. And for so how it is, so it is what is C here. So C is specific, sorry, it is the heat capacity, heat capacity. And what is dt? Dt is the temperature change. So it is the temperature change that occurs when we apply this much amount of heat. Now this is the N is the number of mole. Then what is this heat capacity? This heat capacity is the amount of heat used to raise temperature by 1 degree Celsius or 1 Kelvin or 1 unit, you can say. So this is this heat capacity. So it is the amount of heat which is used to change the temperature of the body by 1 unit. And the amount of substance is defined. If the amount of substance defined, suppose we are taking it for 1 gram, sorry 1 kg, then it is called specific heat capacity. So for 1 kg, it is called as specific heat capacity. Specific heat capacity. When we are defining it for 1 mole, that is called Cm, molar heat capacity. And if we are defining it at constant pressure, then it is Cp, and at constant volume, it is Cv. Now what is the relation for all of this? So let us do it for different processes. So suppose we are calculating delta U at constant volume. So suppose we are calculating it for constant volume and it is reversible for reversible process. So first we will calculate the work done. We know that dW is equals to minus P dV. So if we integrate it in both sides, so it will be, now we are replacing P by nRT by V. So dV by V, that is W is equals to minus nRT ln, suppose this is the limit here, V2 by V1. So this is the work done. So this is for the work done. This is for the dq. Now let us take different cases. And for what is for the reversible, so it will be simply W is equals to minus P delta V. So P is external pressure that is applied. Okay. Now suppose this process is isothermal. So what is the formula for isothermal? So we know that delta U is equals to N Cv dt or delta T, any of this. Now since this delta T is 0, so delta U is equals to 0. What about work done? So it will be simply minus an RT ln V2 by V1. What is about Q? So Q will be same. And if we are calculating it for, so this is for reversible. What is for irreversible? So it will be minus P external delta V. What is the enthalpy change? So we know that enthalpy is equals to N Cp dt. So this again, this delta T is equals to 0. So it will be also 0. So this is for isothermal. Now suppose we take the isobaric case. So what is the case for isobaric? That P is equals to 0. So first of all, del U is equals to Q. Why? Because we know that W is equals to minus P external delta V. So for this reason, it will be delta U is equals to Q. Okay. And at constant pressure, it will be, we know that C becomes Cp, so it will be dt. So you can derive the formula also in this way, delta U. Okay. What about H? So H is equals to U plus Pb. Now since this pressure is constant, and we also know that delta H is equals to delta U is equals to Q plus W. So it will be, this pressure is constant, so P delta V. Sorry. So P delta V. We know the formula of work done, it is minus P delta V. So this both will get cancelled and it will be Q, and Q is equals to NCP dt for constant pressure. Hi Shiv. So students, see here one thing, that I am only calculating the state path here. So we do not need to calculate it for the minute change. We do not need to calculate it like this du, because we know that it is a state function. Good evening, Shiv. So we'll use the formula for you can say irreversible also, and calculate this delta U and delta V. Now this is for irreversible, and for reversible also it will be also 0. Why is it so? Because we know the formula for reversible, it is minus nRT ln V2 by V1. Now since it is V2 by V1, okay, so this is for reversible. Now let us take the isochoric process. Means the volume is remained constant, that is delta V is equals to 0. Now delta U is equals to Q plus W. Again this W is equals to minus P external delta V. Since this delta V is 0, so we will get both for reversible and irreversible, we will get both as 0. So delta U is only equals to Q. Okay, thank you. That is for today's class. Now in the next class, we will study about the spontaneity in more detail and look how that Gibbs-Helmholtz energy is used to identify this spontaneity of a given reaction.